Okay, so today we're going to focus on microwave and LiDAR sensing. And also, just to take a quick look at two example images here. I'm not sure if it's clear enough. Usually the most of the sensing data we talk about today, in addition to the traditional spectral information, they also offer one additional aspect of information. So by the end of today, I hope that is clear. But maybe something you can see here in terms of, in addition to the different colors, there's something else we can see, we can observe actually from the image themselves. So that's actually another component we're going to talk about today. So I want to bring up the review assignment first, so that maybe you can start a new document, a Word document, or maybe a Google Doc to start answering the question for today. So we're going to change the format for this review assignment because originally I thought we can do an online discussion, but I figured we can just do like a Word or a Google Doc write-up as opposed to a discussion, because we already have a discussion ongoing. So this one will only be a regular document. You can start something now so that as we go over things today, you can start doing your answers or taking notes this way. So this review assignment is about compare radar versus LiDAR. And I want you to list at least two similarities and two differences between radar and LiDAR sensing. So what I would do, like if you're starting a new document, I would maybe do a two-column thing. The first column I would do similarities, and the second column I would do two differences. And you can try to do more. Here I'm only saying at least two because I figured it's easy to come up with two, but you can do more. And also it depends on how you break up the information into different items. So this one is due Wednesday next week, so 10 days from today. And actually, if you take focus on the name radar and LiDAR, I feel like you probably have already noticed one similarity. They also, they both have the DAR. So what does that mean? That's actually a very important similarity. So we'll start with some other related concept today. So first of all, I want to talk about passive versus active remote sensing. So in the first two labs, the images we are working with, they are both under the category of passive remote sensing. And actually, most of the image data, for example, those image data you saw, you have been using on Google Earth or Google Map, they're all passive remote sensing. But also there's another group of active. So let's just clarify the difference here, and then we'll talk about some examples. And also you have to probably be very careful when you relate this two category with radar and LiDAR and all this concept that we're going to talk about today. So for passive remote sensing, passive sensors, so they actually measure energies that are naturally available, which means they would rely on some external energy source. And this particular external energy source we're talking about here, it actually refers to solar illumination. So this passive type of sensors, they don't really they just record whatever energy that is naturally available. And most of this visible, optical sensing systems, they operate during the daytime because that's the only way you can see. But also thermal sensor can record energy at night because the thermal energy may be absorbed and emitted at night. Because the object may still have a temperature, and also we talk about the heat release, the heat loss in the urban areas. So either way, those categories relies on solar illumination external source. They are referred to as passive sensors. And the active sensors, instead of relying on this external solar illumination, they actually generate their own energy to illuminate the objects. So which makes them active, and they can just generate their own energy so that they can acquire data anytime, day and night. And there are also something more we'll talk about later today. And these active sensors that basically will have their own energy. So based on the definition and also the distinction here, I have a quick question just to check our understanding of this concept. What do you think? Which category do our cameras fall into? I'm sure you have used a camera. So do you consider the cameras to be passive or active remote sensing sensors?
I would say that they are passive unless you're using a flash.
Andrew, did you say something?
I said passive, unless you're using a flash, I guess.
Okay, so you both mentioned the flash. So should we maybe consider a camera to be both? Because we do have the option to use a flash when it's really dark. So a camera is actually a good example of both passive and active because of the flashing capability. And there's an energy source there. So good. So we're going to.
Isn't every sensor technically passive then? Because is the sensor itself sending out the signal and then receiving the signal back?
We're going to talk about some active sensors today.
Okay.
Yeah. So far, and also most of the images we have seen, they are passive. And also, I would say, I guess for most of you, unless you're going to become a radar image or LiDAR image analyst, in your future, you'll be working with passive remote sensing for the most part. Or maybe you're using a combination of passive and active, but also there has been increasing use of active that we're going to talk about today. So let's introduce another concept called microwave sensing. And in terms of microwave sensing, so here the microwave basically just refers to the microwave portion of the EMR spectrum that we have been, we have been showing the EMR, the whole portion, but we haven't really talked about the microwave portion a lot. So this microwave portion refers to the longest wavelength portion that remote sensing uses, and it ranges from 1 centimeter to 1 meter. So really, like we're not in the micrometer range anymore. So for microwave sensing, we're talking about the centimeter to meter range, something we can really see because they're large enough. And because of the longer wavelengths, microwave sensing can penetrate through cloud cover and also dust and also even some rainfall. So they do have this so-called all-weather capability because they usually function. And also here I'm just making the statement of pretty much everything except for the heaviest rainfall. And each time I got the question of what do you mean by the highest rainfall? So how heavy? It's kind of hard to describe. There's a spectrum of rainfall, but usually microwave sensing functions very well because they do have the capability of penetrating through this particles in the atmosphere, so that you can really observe the ground cover in a better capability. So we talk about the longer wavelengths is not susceptible to atmospheric scattering. And also here I want to be clear that microwave sensing, by the term microwave sensing, we're actually talking about either passive or active. I know today we started with passive versus active sensing, but microwave sensing, this longer wavelength sensors, they can be either passive or active. So please do not get confused. There are passive microwave sensing, but there are also active microwave sensing. They're used in different ways. So let's first begin with passive microwave sensing because after this we'll be focusing on active. So for passive microwave sensing, This whole idea is very similar to thermal remote sensor, thermal sensing systems, because of the longer wavelengths and the energy will get absorbed by an object, and they later on they get re-emitted from the object. And also, again, because of the longer wavelengths, they have better penetration power, but we also mentioned this amount of energy. So because of the longer wavelengths, the amount of energy can be recorded is fairly small. So which means, remember this idea of the field of view, the instantaneous field of view. So in order to record enough energy from this passive microwave sensing, most of the passive microwave sensors has a very low spatial resolution. So which means they need a really large field of view in order to record enough energy so that they can form a usable signal. Most of the sensing systems will be, in this kilometer range. So you'll see a lot of 1 kilometer by 1 kilometer passive micro sensors because of this long wavelengths, and they need a larger field of view in order to record enough energy. And for passive remote sensing, so most of the uses are related to meteorology, hydrology, and also, for example, if you want to detect pollutants in the ocean, like the oil slicks, these are all example uses of the passive microwave sensing. Mostly temperature and moisture properties because of this mode of functioning, and they're being absorbed and then emitted by the objects. So that is briefly about passive microwave sensing. And for the most part of today, we're going to focus on active microwave sensing. So how this function is basically a recording, we know active sensing, they will send out their own energy and then record the energy returned back to the sensor. And we'll count this returned back as back scattered from the terrain or from any object on the ground. And under active microwave sensing, we'll focus on radar. So here is actually where we begin to compare radar versus LiDAR. Please do not get confused when you work on the second review assignment. We're talking about radar. We're talking about active microwave sensing, so not the passive microwave sensing. So radar refers to radio detection and ranging. And also, the DAR here, and especially this R here, refers to its ranging capability. So what this means is because the radar is an active sensing. So by sending out, the sensor sends out the energy to the ground, to the terrain, either the trees or the ground, or maybe the houses, different objects. They can actually measure the distance from the sensor to the objects, because the time delay is recorded. We know how long for the light to travel to the tree and then return back to the sensor. And I assume you probably vaguely remember the speed of light, or remember the exact number. And by basically doing this equation of speed times the time, you will be able to measure the distance. So because of the ranging capability, radar provides another layer of information. In addition to the regular spectral information, we are also able to detect the elevation, the terrain surface, and the different distance attributes, and so that we can better capture the terrain characteristics. And here is just a brief video clip to show you how one of the examples of the SAR radar, the synthetic aperture radar function, and how they send out their own energy, and then how the sensor records the backscattered energy. So the energy comes out at the pulses of energy. So you can really see the individual pulses, and then they'll be returned back to the sensor. And you can still see the color attributes. And there are spectral information to be recorded, but also a radar does record one additional layer of information, which is polarization. We'll take a quick look in a few examples after this slide. So just some general characteristics of radar sensing. First of all, whenever we talk about radar, we know because it's active sensor, it functions both day and night, independent of stellar illumination. Because the sensor can generate its own energy either way, so it's independent of time, independent of the external light source, energy source. And also because of this longer wavelengths of radar, microwave sensing, it also has this all-weather capability, because we know the longer wavelengths can penetrate through cloud cover, dust or any other particles in the atmosphere. And in addition to this time capability, the all-weather capability, radar also provides very good positional accuracy because of the ranging capability. You can measure the terrain features, delineate the very detailed elevation and also the surface characteristics. And actually, radar provides a very good source for generating global digital elevation models. If you have explored the different data sources on Earth Explorer, I'm sure you probably have already used or worked with LiDAR data, either directly or indirectly. If you have heard of the SRTM, so that's a global radar sourced elevation data for, which covers the entire ground, and also the surface characteristics is very different than the traditionally interpolated from sampling, because it can capture more details. If you compare the ground cover, it can really show you the very detailed elevation change or terrain surface change. Just some examples to give you an idea of how radar data looks like, but also what are the additional layers of information radar can provide. And the first one is the Teide volcano in Spain. So they're recording a volcano eruption here, and we can still see the colors. For example, here, I'm not sure how would you describe this color. I would say maybe like green and yellow color. They're showing the lava flow. And here, there are some small settlements and vegetated covers overall. And apparently it's not true color. And we know the computer display will use, again, the three color gamas, red, green, and blue to show three different layers. And here are the three layers shown for this particular radar image. First of all, for the red band, they're showing, the red color, they're used to show the L band horizontally transmitted, horizontally received. And they're using the green color to show L band horizontally transmitted, vertically received. And they're using the blue color to show the C band horizontally transmitted, but vertically received. So, the bands here, they're still corresponding to the different portions of the spectrum. However, radar, they do use one additional piece of information, which is referred to as the polarization. How is the energy transmitted and how they're received back by the sensor. And this, usually there are four types, either horizontally transmitted, horizontally received, or vertically received, or you can be also vertically transmitted, horizontally received, or vertically received. And second example is a radar image of the mountain Everest, and also actually captured through thick cloud cover, but you can still capture the terrain surfaces very in a very detailed manner. And here again, they're using L bands and C bands. We'll look at what the L band and C bands refers to shortly. I'll have a table to show you the wavelengths and also the major uses of each band for radar sensing. And in addition, we see the polarization information once again, horizontally transmitted, horizontally received, or vertically received. So, and those are usually this different layers of information goes with radar data. So based on the examples, we saw both wavelengths and polarization. They are recorded, and also they affect how a radar system sees the ground objects. Because right now it's not only about how they're interacting with different portions of energy, but also they're looking at the polarization attributes as well. And also, I just want to just talk about the big picture idea in terms of the applications of radar. So radar is, getting more popular recently, and especially a lot of researchers are exploring the use of radar in combination with traditional optical remote sensing. For example, they may combine radar data with a high resolution near infrared image in order to capture deforestation in the tropical region. Or some people are basically trying to explore the use of radar in the urban environment. So because of the additional information, the polarization information provided by radar, they're usually used as an additional complementary layer of information with traditional sensing, so that you can use radar to capture information that are not available in the past. And else is primarily because of the longer wavelengths, EMR, and also the polarization attributes. And this table summarizes the different wavelengths portion we talked about so far. So from top to bottom, we're looking at things from relatively shorter wavelengths, microwave portions, to the longer wavelengths. And usually, instead of referring to them using the specific wavelengths portion, we just say, C band, L band, or P band. So P band here is the longest radar wavelengths. And the other bands, as we saw in the other examples, L band and C band, they're also very commonly used. And also one additional piece of information, because we're talking about microwave here. Actually, the microwave oven in your home, they're using the S band as the energy source. And in general, the different bands are used by different sensing systems depending on their specific applications. I'll just, because the band's information, so I would say instead of trying to remember this page, maybe you can just, take a screen capture or take notes for future reference. But I would like to show you an example of just to compare how, the different bands looks like. So once again, we're getting back to the fact of truth that, the penetration power, penetration depth increases with wavelengths. So in this case, if we go back here again, the longer wavelengths, the longest wavelengths radar portion, P band, depending on basically this principle, we know P band will have the greatest penetration depth or penetration power when compared to the local, the lower range band. So in this case, you can compare a image between the P band and the X band. And the P band shows you more details on the ground. So actually, this longer wavelengths radar portion, they're not only able to penetrate through this atmospheric, maybe the particles or cloud cover or other features, but also they have the capability of penetrating the solid features, including vegetation and soil surfaces. So that is to say, the P-band will have a greater penetration power even underground. So this example showing you basically the same area, P-bands gives you more information under the ground surface. And just some quick ideas on the LiDAR polarization. And also, since we're going to move to the final project discussion shortly, I want to just clarify, because LiDAR is a very unique system of remote sensing. So usually for the LiDAR image processing, the techniques are going to be different than the traditional ones we're talking about in this class. So in this class, we're going to focus on traditional passive remote sensing, the optical images, and doing classification and analysis of the spectral information. And in the upcoming lab, we're going to talk about LiDAR. So for your final project, I would recommend not to focus on radar. I mean, you're free to bring in some radar data as additional sources, just to explore the capability and maybe some functions if you're interested in looking at within ERDA's Imagine, but I wouldn't try to focus on radar for your final project unless you're willing to learn a system that is outside the class. So here, just some brief information on the polarization of the radar system. So we talked about the two, the wave model of how remote sensing works, or how to measure wavelengths. And in terms of the radar system, because it's an active system, the sensor can really control how the energy is transmitted, just to filter out and to control the energy to be either horizontally transmitted or vertically transmitted. And when the energy backscattered to the sensor, basically the direction may stay the same, or they may be changed. So in this way, here comes 4 different forms of radar polarization: HHV, VHV, or VH. And that refers to the 4, basically the different ways of how the energy is transmitted and received. And a similar idea to the spectral information, different ground objects, they will interact with the energy in different manners. So basically, for example, some objects, some surfaces, they may bounce back the energy horizontally or vertically, depending on how the energy is sending out. And in this way, this additional layer of information, this polarization will give us some additional information that spectral bands are not able to capture. So that is also the reason why radar images are oftentimes used in combination with the traditional optical images to acquire more information, more data. So a few years ago, we had one student doing a deforestation study in Indonesia. So he actually combines the use of Landsat. Landsat is one of this longer RPAV system that we'll talk about next time. He combined Landsat with some new radar source to analyze deforestation. So not only because it's tropical region, because we want cloud-free data, but also one of the major challenge in the tropical deforested region is they're trying to distinguish between plantations and natural forest, and which is also one of the weaknesses of the traditional optimal remote sensing. So far, we have been looking at near infrared images, and we know vegetation covers, they reflect a lot of near infrared energy. And it's the same case for plantations. So in order to better help capture these different textures between natural forest and the plantations, this radar image source provides very useful information for you to detect the ground objects. In addition to the near infrared, because they may both have high reflectance on the near infrared band. However, radar will help you capture the texture information because they interact with the polarized energy in different manners. Something visually we can maybe we can capture. The plantations tends to be more regular in terms of the arrangement and also their shapes and overall physical appearance. But the natural forest tends to be irregular, but also this types of textural information can be nicely captured through radar polarization. So let me just take a pause here before we move on to the LiDAR part. So far we've finished the brief discussion on radar, and we'll begin with a video to talk about the LiDAR differences. So actually the video will talk a lot about the major how LiDAR works, and maybe throughout the video you can try to list a few things. Just when you watch the video, try to see if maybe you're able to finish the review assignment.
So LiDAR, or light detection and ranging, uses lasers to measure the elevation of things like the ground, forests, and even buildings. It's a lot like sonar, which uses sound waves to map things, or radar, which uses radio waves to map things, but a LiDAR system uses light, sent out from a laser. But aren't lasers used for stuff like, I don't know, scanning barcodes, making your favorite band look awesome, removing hair? Ew. Seriously, how does a LiDAR system use lasers to measure stuff? Now, just for the record, there are different ways to collect LiDAR data. From the ground, from an airplane, or even from space. Airborne LiDAR data are the most commonly available LiDAR data, and airborne LiDAR data will also be freely available through the National Ecological Observatory Network, or NEON, so we'll focus on that in this video. So to get how lasers are used to calculate height in airborne LiDAR, we need to understand the 4 parts of the system. First, the airplane contains the LiDAR unit itself, which uses a laser to scan the Earth from side to side as the plane flies. By the way, for you remote sensing geeks out there, the laser system uses either green or near-infrared light, because these wavelengths or types of light reflect strongly off of vegetation. The next component of a LiDAR system is a GPS receiver that tracks the altitude and XY location of the airplane. The GPS allows us to figure out where LiDAR reflections are on the ground. The third component of a LiDAR system is what's called an inertial measurement unit, or IMU. Not to be confused with EMU, an IMU. The IMU tracks the tilt of the plane in the sky as it flies, which is important for accurate elevation calculations. Finally, the LiDAR system includes a computer. The computer records all of that important height information that the LiDAR collects as it scans the Earth's surface. No computer, no data. It's as simple as that. Now you may be wondering, how do the laser, the GPS, the IMU, and the computer all work together to get us these fantastically useful LiDAR datasets? Well, the laser in a LiDAR system scans the Earth, actively emitting light energy towards the ground. Now, before we go any further, let's get 2 key LiDAR terms associated with this emitted light energy out of the way. So we can speak LiDAR and all. First, let's define the word pulse. A pulse simply refers to a burst of light energy that is emitted by the LiDAR system. And second, let's define the word return. Return refers to reflected light energy that has been recorded by the LiDAR sensor. So pulses of light energy travel to the ground and return back to the LiDAR sensor. Now we're speaking LiDAR. Now all of this pulse and return business is great, but speaking the language doesn't give us height. To get height, the LiDAR system records the time that it takes for the light energy to travel to the ground and back. The system then uses the speed of light to calculate the distance between the top of that object and the plane. So let's break down what this distance calculation looks like. You take travel time, multiplied by the speed of light, divided by 2 since the light traveled to the ground and back. This calculation gives us how far the light actually traveled to the ground. So using this math, we know the distance between the plane and the ground. But we're not done just yet. How do we figure out the actual elevation of the ground? To figure out ground elevation, we take the plane's altitude, calculated using that GPS receiver. And then we subtract the distance that the light traveled to the ground. And that covers the basics of how a LiDAR system uses lasers to measure height. So now we've got the basics down, but there are two more things that a LiDAR system has to consider when calculating height. First, the plane rocks a bit in the sky as it flies due to turbulence in the air. These movements are recorded by the Inertial Measurement Unit, or IMU. No, not EMU, IMU, so that they can be accounted for when height values are calculated for each LiDAR return. And also, an airborne system scans the Earth from side to side to cover a larger area on the ground when flying. So while some light pulses travel vertically from the plane to the ground, or directly at nadir if we're still talking LiDAR lingo here, most pulses leave the plane at an angle or off nadir. So the system also needs to account for pulse angle when it calculates elevation. So let's put this all together one last time. The LiDAR system emits pulses of light energy towards the ground using a laser. It then records the time it takes for the pulse to travel to the ground and return back to the sensor. It converts this time to distance using the speed of light. The system then uses the plane's altitude, tilt, and the angle of the pulse to calculate elevation. It also uses a GPS receiver to calculate the object's location on the ground. All of this information is recorded on that handy-dandy computer, also mounted on the airplane. And that, my friends, is how a LiDAR system works. Now, there is one more component of a LiDAR system that makes it so useful. A pulse of light doesn't just reflect off of one thing, like the top of a tree, and yield one return. Sometimes a LiDAR pulse travels through things, like the gaps between tree branches and leaves. Think about standing on the forest floor and watching the sunlight filter through the tops of the trees, making the leaves and branches glow. So light energy that passes through the canopy reflects off of the branches and leaves within the canopy. This ability of a LiDAR system to travel through and record information starting from the top of the canopy, through the canopy, and all the way to the ground makes LiDAR systems unique and highly valuable to scientists studying trees. These returns from within the canopy tell us more about what's happening inside the forest, or the forest structure. For example, they can tell us about the shape of the trees, or the density of the leaves on the trees. They can sometimes even be used to estimate whether there's shrubs below the trees on the forest floor. But we'll save that topic of using LiDAR to estimate forest structure for another video. And now, my friends, you know how a LiDAR system generally works. And also, you can consider yourself fluent in the language of LiDAR.
Okay, so basically this video covers all the basics you really need to know. And I do like they break down the mathematics a little bit better to talk about the ranging capability that we actually have been talking about for radar. So I hope you have kind of like have your nose finished in terms of comparing between radar and LiDAR. So LiDAR refers to light detection and ranging. So we know it also has this great ranging capability for you to measure elevation or measure height of the ground objects. LiDAR is also an active sensor that will transmit energy and basically in the form of laser to the ground and then measure the time travels back to the sensor from the object. We know the calculation, and also another important difference between radar and LiDAR to take notes of is the portion they use. So we know radar uses the longer wavelengths. However, LiDAR use laser technology that they focus on the optical portion. So mostly, depends on the application. If they are mapping things on the ground, like maybe the ground cover, the buildings, the trees, they will be using near infrared region of the energy. However, if the major use of the LiDAR system or the LiDAR project is to analyze bathymetric features, which means underwater ground, they may focus on blue and green region. But either way, keep in mind that LiDAR uses shorter wavelengths because of, they're trying to use the highly intense beam to analyze the ground surface. So mostly they're either blue and green for bathymetric applications or near infrared for topographic applications. So for in the new lab 3, we'll be using a S3 lesson to learn how to use LiDAR to classify between different ground features. Like tree, we don't really focus on trees, but mostly ground cover, and also delineate very detailed 3D building footprint from LiDAR data. And in terms of how the LiDAR data looks like, they're actually in the form of 3D point cloud. So each point will have X, Y, and Z coordinates, which records their 3D location in, basically on the ground. For example, the X, Y location just refers to the actual geographic location, and the Z is the height information. And the raw LiDAR data usually comes in the form of multiple layers, and also when you zoom in very closely, you just see really a cloud of different points, and you can classify them, and you can separate the different points depending on their spatial characteristics. The video also mentioned another great capability of LiDAR is their multiple returns. So basically, because of the energy is highly intense and highly focused, and they can penetrate through the gaps within, the tree leaves and tree branches, and to reach the ground. So that is also why the LiDAR data usually comes in the form of 3D point cloud, because not only just capture the top canopy cover, they can really get into what's underneath the tree cover, and so that you may have a layer of ground, you may have a layer of the low trees, you may have a layer of the high trees. And also some other classification algorithms would allow you to analyze the spatial characteristics. For example, if you see the size of a building, you can further classify them into different buildings, and you can also get rid of the noise depending on the empirical knowledge that you learned from a study area. So the multiple returns of information of LiDAR is very valuable because we're dealing with a large amount of data, millions or even billions of points, and you have to really be able to separate them before you can make meaningful analysis. So actually in the lab, you folks will see an example when they classify buildings from the whole cloud. The first thing they do is they classify the ground, basically the last return of all this LiDAR point cloud. Once they extracted the ground cover, among all the points, they will consider the whatever surface that only sent back a single return to be buildings, because they would consider tree covers can give you multiple returns, because usually the energy can travel through the tree covers and reach the ground, or maybe reach a lower layer of objects. Whenever you see a single return, that means it's likely to be a building. But of course, you have to offer additional information. For example, in the study area, the buildings usually ranges between a certain height, and also the buildings usually comes within a certain size. So with the additional spatial information, you're able to classify LiDAR data, and so that they can be further extracted into three-dimensional features. And also some applications of LiDAR, and since right now, in Chicago, we have LiDAR data available, and eventually we'll have LiDAR data for the entire United States. And so far there are, I'm sure you folks heard about the Mayan region, where they did this whole laser scanning and discovered this whole hidden Mayan settlements, which is way beyond our understanding previously. So it's all depending on the LiDAR data. And those are, depending on the project progress, they may release the data. So I found this LiDAR data set for Belize, which is available through a website called Open Topography. So Open Topography is one of these interesting sites you can obtain project-based LiDAR data. So those are usually, say, obtained or collected through a research grant, and then after their research, they decided to release the data. And the national map, we'll talk about some different data sources next time. There are some LiDAR data available. So within the urban environment, LiDAR has been used for building the urban 3D models. For example, you will learn how to extract building footprint, which is an important data source from many major cities, how to extract urban footprint data from LiDAR. You can also build more detailed 3D urban models for planning purposes or for flood modeling. Another example mentioned in the video is about forest tree inventory. You can measure tree height, tree structure, density, the shapes and different species. And there are also some research focused on tree identification through LiDAR, because with LiDAR, you can really capture the individual trees, the detailed three-dimensional model. So that will give you some opportunities for identification, automatic identification. And another great use of LiDAR is to provide highly detailed, high-resolution elevation data. So now through the national map, we have 1 meter elevation model available. So wherever you see this 1 meter resolution elevation data available, DM data available, they're usually be captured through LiDAR. That would allow you to look at terrain surfaces, elevation features at highly detailed manner. And here are just some major data sources for today. And next time, we're going to talk about where to get different data, including radar and LiDAR, but also some optical remote sensing. So next time we'll talk about more satellite and data. But for today, if you're interested in getting started, maybe to take a look at what are available, 3 important sources, as I think I mentioned 2 of them. And the first one, actually Sentinel-1 from the European Space Agency, ESA. The Sentinel-1 is a radar source. It's fairly recent. So basically it's a global coverage, Sentinel data, higher resolution. And for the USGS, the national map, apparently it's for the United States. So there are some DM data and LiDAR data available. LiDAR is not national coverage yet, but I think at least for Chicago is all covered. And Open Topography is another LiDAR source available. And let me also, do you folks have any questions?
No, I don't have any questions, but I just wanted to say, kind of related to current things like LiDAR is used by autonomous vehicles to navigate.
Right.
LiDAR,
yes.
They've actually added a LiDAR sensor to the new iPhone. So
yes,
LiDAR is becoming really popular because it's something that shows us a lot of detail, and it's relatively easy or inexpensive to use for us. So
yeah, and also kind of related to the automatic cars, because I attended this grand opening of HERE Technology a few years ago, but they were showing some of their projects. Of course, LiDAR is used in developing their system for automatic driving cars. But in addition to LiDAR, you can really see this a great use of all different layers of GIS data. So in addition to LiDAR, they're also using, like thousands of different layers of information they can identify just in combination to provide better accuracy. For example, the location of individual facilities, and of course, the street data and other, like housing data and other elements. Okay, so that's about radar and LiDAR, and in the lab we'll be talking about basically looking at LiDAR using ArcGIS Pro, and I hope you all had Pro running up properly. So for the new assignment, just a quick reminder. So we are working on Lab 3 this week using Pro, and I know some of you are new to. None of you is new to GIS, but some of you may be new to Pro. But I also want to mention just something about this transitioning time. So ArcGIS Desktop will still at least function until 2026 by their recent plan. So which means in the next 5 years, 6 years, let's say 5 years, likely you will have to, I'm sure in the next 5 years, some of you will have to, start getting jobs and all that. So I'm sure depending on where you work for, they may, still in the transition between desktop and Pro. So I think it's important for you to, kind of learn both. But of course, you have to, if you have learned desktop so far, try to transition to Pro, because eventually there will be no ArcMap, ArcGIS desktop anymore. So everyone will switch to Pro, and it's still the same core, but the interface is different. So I would say, we'll use this lab to get started with Pro. And actually, I posted a course on D2L, the cartography S3 MOOC course. I think it's also a very interesting way to learn Pro through their cartographic capabilities. And for review assignments, the second assignment, like I mentioned, it's not an online discussion anymore. It's going to be a write-up. So I posted a folder on D2L. So please, if you have something ready, maybe you can just throw in what you have taken so far and get it done. We do have the first online discussion assignments due this Wednesday. So please do if you haven't, because everyone will have to respond to another person's post. I know we have a couple so far, but if you haven't done, let's try to get that done as soon as possible. We also have the image resolution lab due this Wednesday as well. Okay, so if there's no questions, but feel free to bring up if you have any. Let's talk about the final project. So I will send you, the final project guidelines is posted on D2L, but I'm also sending you a copy of the PDF version in the chat so that you don't have to log on to D2L. Let me bring up my, I think it's here. Okay. So for the final project of remote sensing 390, basically, you're going to work on a remote sensing based project for a geographic or environmental problem. So that is pretty much to see anything that you can apply image processing techniques. I know so far we have been really focusing on the concept, the different conceptual and theoretical issues, the principles, and talked a little bit of the data, but we really haven't touched too much upon what data are available, what are the major applications. But the reason why I want to just get this talked about earlier or started earlier is just because I want you folks to maybe have something in mind as we learn more techniques or applications. So very similar to other GIS classes, you will have to give a presentation in class and write a final paper. And the report is pretty simple. I'm only looking for a technical report that is 6-page long, double-spaced from each group. You can go beyond, and I'm sure you will go beyond. And usually I have papers that is, 8-page, 10-page, 15-page. So, this 6-page is not something you have to worry about. I'm sure you'll have enough to talk about. And one specific thing is, for example, if you're working in a group of 2, I'm looking for each person to process at least 1 image data file. So that is to say, even if you're working in a group, you will have to do something. It's not like, okay, for example, I'm working with Daryl, and Daryl, you can just go ahead and process all the data. I'll be just writing the paper. It's not like that anymore. You have to process your own data. And maybe for the paper, you can try to, break up and to say, I'm going to talk about my procedure, and you can talk about your procedure, and we can work together on the, results summary. But either way, everyone has to have some hands-on portion. Like if there are 3 people in your group, I'm looking for at least 3 processing products, 3 different images. But also, this part we can talk about. It's possible that, for example, the 2 of you are working on the same image, but you use different methods. That is possible. So here I just want to give a general idea, but I'm flexible as long as there are something for you to do. Here I have the timeline. So I'm trying to push this forward. However, once again, I'm flexible. So right now the plan is you will have 10 days from today until the end of next Wednesday to think about a topic, and of course to figure out who you will work with. I feel like 10 days is long enough, but also, because we're doing things remotely, I know it's not as easy for you to maybe just talk to the person sitting next to you, or, this gets really tricky. So I'm flexible if you need more time on that, because we're still early. And in terms of what you can work on, I know it's probably your first remote sensing class, and it's your only remote sensing class, and you probably have no idea what you can do. So here I give you a list of possible topics you can just take and go. And also this project is, so it doesn't really matter if 3 or 4 groups doing the same project. It's okay, because it's a matter of getting the hands-on experience. So you're free to choose one example from here if you just have no idea. For example, if you're interested in LiDAR after today, maybe you can take a look at using LiDAR data to measure, tree canopy colors, density, tree structures, or you can maybe analyze other more general features, urban growth, deforestation, vegetation mapping, hyperspectral sensing, for example. There are a couple more, and eventually we'll cover all that. And in terms of the general ideas, I can think of 3 general categories of research you can choose to work on. So the first category is, the utility and applications of remotely sensed data. So in the first category, to me, it's more about exploring the usability, the utility of some special sensors. For example, hyperspectral sensing, LiDAR, thermal, nighttime, or drone image. Right now, because we really couldn't go to campus and collect some drone images, but there are some free samples online that if you're interested, there's a possibility. And second category is about technical, the perspective of, like basically you explore the different techniques, and you don't really care you're doing urban or deforestation or agriculture, but you just want to go with more technical components. It's also possible that you can focus on image pre-processing, image classification, and change detection. And we'll cover the 3 categories of techniques later this semester. In the last category, the third category I can think of is basically the general applications. For example, for you folks who are, basically you're here for, the geography and environmental studies components or science components. You do have something in mind that you really want to study. For example, maybe you're interested in urban issues, and maybe you're interested in weekend laws, and maybe you're interested in climate change, terrain surface mapping. So you can focus on this particular application and then see how remote sensing can be applied in your area. So for example, you're interested in urban sprawl, and then you can explore the use of remote sensing for mapping or characterizing urban sprawl. So here are, again, some example topics for you to just, get started. And for now, the plan is we're going to use Lab 4 to collect your data. I feel like I probably have to extend the deadline just to give you folks some more time to, think about what you want to do and maybe find someone that you can work with if you're looking for joining a group or form a group. But for Lab 4, what you need to turn in is your data. And also I'm looking for individual submissions, even if you're working in a group. But that part we can talk about. Depending on your topic, maybe there's only one data available because each individual person within the group may work on different procedures or apply different methods. In that case, it could be just the same data source. So right now I said due February the 17th, which we can extend. So once again, I'm flexible. And I think after this primarily will be, we have a early midterm exam schedule. So, that's also the reason why I'm thinking we can try to get this done earlier, because after that will be midterm and then, maybe a little break after the midterm and then the spring break. So after the spring break, we can focus on just to make progress and, develop more detailed plans and procedures, image processing techniques. So we'll have 3 days scheduled for the group work or just individual work. And presentation is 1 day. We have 11 people this time. So, I'm not sure how many projects we'll have eventually. So that part we have to figure out, depending on how many projects, how many presentations we have, we can figure out the format and also a time. But for now, let's say just focus on selecting a topic and then figure out whether you will go solo or you want to work with someone else. And the reports is due 2 days after the presentation, just so that you get some time to maybe finalize or, tweak a little bit of things or just wrap things up. For general sections, I'm recommending to be included in your report. And finally, the table is the grading rubric. So let me see. The data processing portion is going to be graded individually, and there's also a peer evaluation portion. So together they take 60%. So I would say at least 60% of the project is graded individually. And also depending on the topic you selected, the results portion may be graded individually. So really, it's even if you're working in a group, there will be some individual work components and individual grading components, which I hope can make things more flexible. And let me also, do you folks have any questions on the requirements or the, or the general schedule? I may have to extend some of the deadlines, so that we have enough time to figure things out. But if you're okay, if you're able to get things done early, that will be the best. So I'm not sure how many of you are looking for maybe working in a group. So I started this Excel, the spreadsheet on Google Spreadsheets, and I sent you the link in the chat, which I think I set up the share setting to be anyone can access with the link. So this document is for those of you who are looking to join or work in a group. So if you're okay, or if you have decided to go solo, you can ignore this. But if you want to work with someone, or if you're still looking for maybe people you can collaborate with, I'm thinking we can start here. Hopefully it works somehow. So for example, if Simone has already put her name down, so you can do this. For example, if you have no topic idea, maybe you can just put your name in one of the number 1 cells. But if you do have a topic, you can also mention the topic and then your name, so that people can keep adding their names to it, just so that people share similar interests can work together. Or for those of you who do have a topic, after putting your topic and wherever you see names that are scattered somewhere, you can just grab their name in here. So I guess it's two ways for those of you who just do not care about a topic. You just want to work collaboratively with some other folks, and just so that you get this additional layer of verification or some support, or you have a topic that you're just looking for maybe one or two other people. So, and also once your group is finalized, you can delete your group so that there won't be any other names or confusions about what's going on here. Yeah, so that's just something I'm thinking we can use to get started. So how many of you are hoping to work in a group? I know Simone is definitely looking for, because her name is here. Rob mentioned a few, maybe last week or 2 weeks ago. Or some of you may still be deciding. So we have 3 or 2. Well, actually, somehow another clock is fairly slow. Okay. We have 1 minute left, so we don't really have time to check in. So maybe Wednesday, I'm thinking we can begin with like a 5 or 10 minutes breakout, just for you folks to have an opportunity to interact with other folks within a smaller group and see. Maybe there will be a brainstorm of ideas, or maybe you can find out some other people that you can work with. Okay, so that's what I have for today. And before Wednesday, make sure to have your ArcGIS Pro installed. And also you will want to use your NEIU credentials that are assigned, which probably shouldn't matter, but for consistency, you will really want to use the NEIU followed by a number to use Pro. And let me see, is there anything else?